excite certain dominant modes. The more general case of a periodic excitation would be perhaps where you drive your car over a railroad track and you're hitting the ties at given spacing. Now, you wouldn't get this sawtooth, but there are problems where this could occur. Periodic solutions often are just made up by sums of harmonic solutions with the right frequency distribution. I don't study periodic solutions as a special case in this lecture series, therefore, because in linear systems it's just a superposition of solutions. Transient problems are those where the force has some finite start and stop time, and often this is a short time with respect to the system's response, and then we might call it an impulsive problem. If the single event is rather sluggish and long like this, then you might find the response of the system would approach a quasi-static situation where the restructure would just give some kind of a response at some different amplitude, but because of a dimensional difference here between the force and the displacement response. But that's a relatively simple problem for the relatively slow force changing, and that could be studied in a quasi-static way as well. Stationary random problems are like airplanes hitting turbulence in clear air, or automobiles driving over rough ground. You can predict some of the averaged values of the structural response by using this kind of an approach. Random problems, we have truly random force here, where you have a perhaps no force for a while, and then something that looks vaguely stationary random but perhaps goes into something deterministic and so on. This is impossible to handle, so we won't study that. By definition, it's impossible because a truly random force is impossible to predict. The general structural dynamics equation of motion has 4 terms in it. We have an inertia term, a velocity-dependent term, typically damping, and then an elastic term here. Sometimes this velocity-dependent term has some gyroscopic or Coriolis effects in it. The force function here is considered to be known in the standard presentation of the equation, and then the unknown is the displacement field. Now, if you're doing a transient problem, these displacements at the nodes are actually joined by the unknown variables on velocity and acceleration. So when we get to that point, it turns out there are a lot of unknowns in the time integration of a transient problem. One simple case for this equation is when you drop out this velocity-dependent term, throw away the external forcing, and you're left with a balance between the inertia forces and the elastic forces. And when you do that, you can then assume that the nodes are going to oscillate in a harmonic time dependence. When you put this cosine form into the original problem, the cosines cancel out as you go from end to end on the problem, and you're left with this static equation below here, where you have only the spatial coordinates at the nodes. And then you get the balance between the stiffness terms and the inertia terms. The frequency of oscillation shows up at this point, and often that term's called the eigenvalue. There are basically 2 kinds of solution processes that are needed in structural dynamics. One of them has to do with the forced oscillation, which is an input-output problem or a response problem, and then the other is the eigenvalue problem that we mentioned. The response problems would occur when you have the frequency response. That means response to a harmonic force, or a transient response, some kind of impulse, or the stationary random response problem. Eigenvalue problems are much different. To do those problems, you need to have an eigenvalue analysis, and we're going to look at that in detail. If you've only done linear statics, this becomes a very novel idea to you. All I can say is that eigenvalues are present in the world throughout us. Some people call them characteristic numbers, latent roots. They're different names, whether you're in a sociological field or engineering or math, chemistry, and so on. But these usually are characteristic numbers that pop out of a given system. For us, it's a balance between the mass terms and the stiffness terms. If there is a Coriolis or a gyroscopic effect, then you sometimes get into complex eigenvalue analysis. This can also occur in aeroelasticity, where you have complex stiffnesses, so that the airstream is putting a springiness into the problem, and sometimes at a time phasing that makes it not look like a conventional stiffness. When I started to work on the finite element structural dynamics problem years ago, I wondered about the dimensions in units. And it took more time than I thought to straighten that out, because the system of units that was being used centered on newtons, millimeters, seconds. And then I needed to find out something about the mass unit and realized I was a bit adrift. Well, many of you may know that mass is really defined in Newton's second law, F equals ma. And when you choose units for your other quantities, notably the length, then you have to have a consistent mass measurement, which you might call a derived unit of mass. In addition, there are two approaches to how you handle your dimensions in the problem. Let me state that dimensions are different than units. Dimensions mean force, length, time, and those are the general characteristics that are handled in similitude and other dimensional analysis problems. Well, one group of people, namely structural mechanics people, tend to work with force, length, and time, and then they eliminate mass as soon as they can as a dimension in terms of the other three, using Newton's law. People in fluid mechanics tend to use the absolute system, where they use mass, length, and time, and they eliminate force as soon as they can in terms of the other three, using Newton's second law. So this is interesting. I hadn't even realized that we had a special name for what we were doing. Once you decide if you're working in gravitational or absolute dimensions, then you need to pick out units. The set of metric units that I've alluded to, I've now called finite element units. Those are the ones based on millimeters and seconds and newtons. And then we'll talk about the mass that is derived in a minute. The System International is a general approach where you deal with Newton second meters kilograms. And surprisingly, one of those is in a 1,000 unit at the outset, and the others are direct units. Then the System International people encourage the engineers and scientists to only use systems of units that differ by a factor of 1,000. So that means the centimeter is pretty much dead. Things like dynes and centimeters and who knows what, furlongs and fortnights, I guess. We want to use a finite element set of units, which is really a special case of the System International units. Now, we used to use conventional units in English. Fluid mechanics people do this a lot yet. That would be foot, pound, second. And then some of you know that the derived mass unit that goes with that is the slug. Many people, however, work with what I call the industrial version, which is the inch, pound, second. And then, interestingly, the derived mass unit is a so-called slinch, or slug inch, which would, on the Earth's surface, weigh as much as 386 pounds. So when you go to a smaller length scale, like an inch, then you get a larger derived mass unit. I've put these different systems into a table in the next figure. Here I have the metric and the English side by side, and then above and below gravitational and absolute. The one that we're most interested in is this set of finite element units here, newtons, millimeter, and second. And now I have given you the answer that the derived unit of mass is the megagram. And I'm sure you're saying, big deal, megagram, bazilligram, who cares? But a megagram is a metric ton, is our reference unit of mass. And the reason that people have chosen millimeter as a reference unit of length is because they don't want to use so many decimal zeros when they're defining, say, the stresses in a camera. If you're at Eastman Kodak and trying to find if your camera is going to break when a gorilla steps on it or whatever, then you want millimeters, a small unit. But now you have to, in dynamics, you've got to measure the inertia of things according to how many metric tons they weigh. So the shutter, is flipping, and you say, how many metric tons is my shutter? Well, that paradox just blew me away when I started doing this work. It must be 25 years ago, and I phoned some companies and I said, are you sure you want to do this? Is this the right way? Well, it turns out that as long as the dynamicist knows they've got an awkward mass set of units, we're going to let the static stress people win this battle and use a tiny measurement scale. Here's the slinch over here that I had mentioned earlier, the slug inch, and here's the slug in the English measure. Fluids people pretty much, I think, are going with kilogram meter second. And I tend to do that on my thermal problems like heat conduction and heat transfer as well. The general purpose computer codes that are used, such as MSC Nastran, do not have embedded constants in them. So as long as the user uses a consistent set of dimensions and units, then there's no problem. So there isn't such a thing as a metric version of Nastran or an English version. For most of our problems, then, we're going to use millimeter, newton, second sets of units. If we go further, though, on this, in our finite element metric system, we need to talk about pressures, which basically are newtons per millimeter squared for us, but that's the same as meganewtons per square meter. And a newton per square meter is a Pascal. And so the relevant pressure scale for us, or the unit, which is a scale on this quantity, is a megapascal. 1 megapascal is 1 MP equals about 145 psi for those of you in the English measure system. I think we need to call it the American measure system now, since our country is one of the few that still uses the older English system. And it's converting rather rapidly now. But the numerical value for mass makes density be kind of a tough quantity, because that becomes newton second squared per millimeter to the fourth when you want to convert to our system, to our gravitational system. And the proper density then is megagrams per millimeter cubed. So how many metric tons can you put in a millimeter cubed, which is a tiny, tiny little fella sitting here? So I consider that an awkward set of units. It's in terms of mass, but it's okay. We get rid of mass anyway as soon as we can. But mass is 10 to the minus 8 typically for a lot of materials. Very, very many zeros. One way, if you want to check some of these ideas, is to use Newton's second law, but put it into numerical form, and then you can see the connection between pounds of force, slinches, accelerations. Over here you have the metric version with 1 Newton is 1 megagram now times 1 millimeter per second squared. I would guess my advice on dimensions and units is to use one consistent set of units and learn how to convert from using the Newton's law in your set of units to get rid of mass when you don't want it, and so on, and then stick with that set of units. Let's have a simple problem session now where we'll look at the conversion of units from one system to another. The problem statement is that there's a certain plastic that has a specific weight, and that's in pounds force per inches cubed. But let's convert that into density in units that are suitable for finite elements, say in English pound second squared inch to the fourth, or metric in megagrams per cubic millimeter. Now, specific weight, as it starts off, has the wrong dimensions. It's not a density quantity, it's a force per unit volume as measured on the Earth's surface. So to get density, first of all, you really need to correct the dimensions of specific weight by taking the specific weight over the acceleration of gravity. Let's work out the equations for these conversions. The general law would be that density is specific weight over gravity. Then we put in the specific weight here in the English measure that was given, and then divide by acceleration of gravity, 386.4 inches per second squared. When you get done with that, you have this number 0.000129 in the units pounds second squared per inch to the fourth. Now that's the thing that we call slinches. When I work a problem out, though, I always immediately get rid of slinches and put it in pound second squared per inch per fourth, as you do in the gravitational approach, the gravitational dimensional approach. Now, if we want to convert further into a metric system, what you like to do is take something that is dimensionally correct, such as this representation here, and then change units by multiplying by 1 as many times as you need to cause the final answer. In our case, you divide by the quantity you're getting rid of, the 1 pound, to eliminate this, but we know there are 4.451 newtons per pound. So that ratio is just like multiplying the number by 1, but it effectively gets rid of pounds here with this one. We now, in essence, by putting these two terms together, have a quantity in Newton second squareds per inch to the fourth. But now we have to correct the length scale. And we know that 1 inch is the same as 25.4 millimeters. In this case, the inch appears to the fourth power. So I raise that number 1 to the fourth power and cancel inches to the fourth against inches to the fourth. And now we have our final answer. We multiply all the numbers out, and we get this number times 10 to the minus 9th Newton second squareds per millimeter to the fourth. And that would be equivalent to megagrams per millimeter cubed if you were using the absolute system as fluids people would use. But structures people tend to use this in terms of force, length, and time. The dominant idea in this lecture is a comparison between the older lumped mass approach and then the newer consistent mass approach. I'm going to start off with a review of a single degree of freedom system so that you will remember some of the major features for that simple spring mass damper system. Then we'll go into the details of the lumped mass approach. I'll talk about consistent mass, how it's derived, and give some fairly involved examples of what it can do. And then we'll have a problem session with 4 problems in it. Let's review the single degree of freedom system as an example of a simple oscillator. This will have a point mass, a spring, and a viscous damper. The spring symbol is this ziggy-zaggy line that looks like a coiled spring from the side and is universally used. The symbol for a linear viscous damper is the dash pot symbol, literally representing a pot of oil with a dasher in it. I've made such dash pots and they really work. They really are linear. The mass, although it's shown as a larger elliptical body, is meant to be a point, and we're only interested in its motion along this u direction. That would be measured from rest. Gravity is usually neglected in this problem so that we aren't worried whether this is vertical or horizontal. The external force is shown. It's relatively easy to derive the equation of motion by giving this mass a positive increment in displacement, velocity, and acceleration. You then find there are these mechanical forces that oppose that motion, including the inertia, the damping, and the elastic forces. The driving force is this function of time, which is presumed to be given. Now we're going to look at this problem for both free vibration and then forced response cases. The first case is free vibration, and that's where you set the damper to be 0 and remove the external driving force. You then have this simpler equation, and the question is whether the inertia forces can be balanced by the elastic forces at all points in time. Because this is a linear ordinary differential equation with constant coefficients, one common solution approach is to guess an answer with some undetermined coefficient in front and then some functional form here. Now we know that the cosine function, when two derivatives are taken, yields a cosine function again. You will get a minus omega squared pulled out of that derivative, and that has to be accounted for. This omega that we've included is in fact going to be related to what we call the eigenvalue. It is a frequency of oscillation in radian measure. And when we put this assumed solution into the two locations in the differential equation, the equation expands into this form. The constants now can be collected, shown on the next figure. The cosine term that's common to both of those force balance terms can be canceled under the concept that you don't want it to be the thing that causes the equation to be 0 at one specific instant of time, which will happen now and again as time marches on. But we want this equation to be true for some interval of time from the present into the future. So the cosine term cannot do it, and we cancel it out. So we look to this set of coefficients to try to make the left side equal to 0. There really are two solutions. This is a bit unusual if you think about linear problems, but we're talking about linearity now in the sense of a parameter dependence on the frequency, for instance. And in that sense, in the parameter space involving frequencies and amplitudes and so on, this isn't a typical problem that we've often looked at in the past. It is instead an eigenvalue problem. Now the one possibility is the trivial solution where the amplitude of displacement u0, and it's really the half amplitude of this oscillation, could happen and is a solution at any frequency. And that's where we get the horizontal red line on this chart below. That trivial solution is not what we're looking for. Instead, we're looking for this second solution where if the frequency omega takes the specific value square root of k over m, then the left side of this equation up above is going to be 0 at all times, all instants of time, and that is a solution. Now that parameter dependence here, which tells you what the eigenvalue is pointed out here, and your amplitudes then, u0 can take any arbitrary value up and down this second branch of the solution. When we take that eigenvalue and put it back into the time dependence and into our general form, this is our solution. One thing that happens in linear eigenvalue problems is that you do not get an exact value for this response amplitude. In other words, this spring mass damper system with the damper removed can oscillate at an arbitrary amplitude. It's assumed that that's small, though, and so we really limit ourselves on this branch to oscillations that keep you within the linear range. The eigenvalue problem that we've just discussed points out some of the system characteristics. The frequency that you get, which is a natural frequency, is a measure of how stiff the system is compared to its own mass. So many people are interested in such a frequency of a system, particularly the lowest frequency when you have a number of those frequencies. Sometimes the eigenvalue is taken to be the frequency squared, or some frequency squared times some other system parameters. But the general concept of the eigenvalue problem has been laid out. Now the next thing